A-level chemistry students, are you struggling with the topic of transition metals and complexes and the aqua ions? Then this is the video for you because I will go over some of the past paper questions related to these topics. And I'm going to start with the 2024 papers, and this is from paper 1. So this question was about the aqueous ions of the iron, of the metal iron. And the first question is asking you to draw the structure of the complex that is formed between the iron 3 plus ion and the ethane diuate ion, where this is the bidentate ligand that is going to replace the monodentate ligand, which is water. Remember that ethane diuate, the structure of ethane diuate has two carbonyl group, and attached to each is an oxygen with a negative charge. The charge of this is 2 minus. So let's draw this one. It's going to be octahedral, as we know. So there will be 3 molecules of the ethane diuate ion surrounding the iron, or making coordination with the iron. With each of these will look like this. So this is the first one. And then the second one with the 2 oxygens, and then the 2 carbonyl group. And finally, the last one, 2 oxygens and 2 carbonyl group. And don't forget the charge for this one. So the iron itself is 3 plus, and we have 3 of the molecules of the ethane diuate, which each 2 minus. So in total, it's 6 minus. So the total charge of this complex is 3 minus. The formation of X is an example of chelate effect. Explain the meaning of chelate effect. When you refer to a chelate effect, there are two things that you need to mention. First of all is that chelate effect means that a bidentate or a multidentate ligand is replacing a monodentate ligand to form a more stable complex. The second point, you have to refer to the stability of this complex, because there is a decrease and there is an increase in the entropy of the system. Anything that refers to the increase in entropy will give you the mark for this one. So you could either say increase in entropy, you could say the delta S is more positive, you could say that there is more disorder, or you could say there are more particles formed. So the answer for here, so chelate is when a bidentate or multidentate ligand replace a monodentate ligand to form more stable complex. And then don't forget to say because there is an increase in the entropy. The following question was a 6-mark question, and it was about the use of the transition metal iron as a catalyst in the reaction between peroxide sulfate and iodide to make sulfate ion and iodine. And this question, they ask you to include a sketch graph to show how the concentration of the peroxide sulfate ion changes over time, and explanation of how the iron 2 plus ions catalyze the reaction, including equations, and finally the overall equation for the reaction. So there are 3 stages here, and we need to include all of them to get the 6 marks. First of all, let's start by drawing the graph, and don't forget to label both axes, the x-axis and the y-axis. So on the x, it's time, and on the y, it's going to be the concentration of the ion, SO8 to minus. Don't forget the brackets that refers to the concentration. And then you're gonna draw the change in the concentration with this graph, or with this line, which shows a decrease in the steepness of the curve. And that will get you the first one, the first stage, or the first 2 marks of this question, basically. The second one will be the explanation of how iron is used. So you have to refer to the fact that the original uncatalyzed reaction is very slow with a high activation energy because of the negative charge on both ions, so they repel. So you can first refer to that S2O8, 2 minus, and the iodide repel each other because they both have negative charge. So the reaction is very slow because there is high activation energy. And then why the iron is used as a catalyst? So the iron 2 plus can attract the S2O8 because they have oppositely charged, and that lowering the activation energy. And then you have to also refer to the fact that the iron has a variable oxidation state, or the iron is going to be oxidized, the iron 2 into iron 3. So you can simply just write the equation for the oxidation. So Fe2 plus change into Fe3 plus an electron. And then you need to start now writing the final stage, the different equations for this catalyzed reaction. So the first one is the reaction between the Fe 2 plus and the sulfur S2O8 2 minus, and that will give you 2 of the Fe3 plus 2 of the sulfate. And then the second stage, when the iron 3 plus reacts with the iodide, so give the iodine plus 2 of the Fe2 plus, and then the overall reaction because they asked for it. So it's going to be S2O8 2 minus plus 2 of the iodide will give you the iodine plus 2 of the SO4 2 minus. So that if you put the answer like this, that should give you all the 6 marks because you covered everything basically. The next question was about the substitution reactions for the complexes, the aqua ions. So the first one was the when you add a dilute ammonia solution to a solution containing the iron 2 plus aqua, or the one which is the aqua ion. Give the formation of the precipitate that forms. So here we know that if you add dilute ammonia, or if you add with the iron 2 plus, if you add dilute ammonia, or if you add even concentrated ammonia, or if you add OH, either dilute or concentrated, you're going to end up with the same product, which is the iron hydroxide. So the precipitate formed here is going to be FeOH2, this is the iron 2 plus, and H2O4. So basically, it donated 2 of the protons from 2 of the OH molecules. And this is a green precipitate, as we know. The student then adds sodium carbonate to a solution containing the equiion of iron 2 plus. State one observation the student would make. We know that with the iron 2 plus, when you add the carbonate, it will give you the carbonate of the iron, which is a green precipitate. But if it's iron 3 plus, it's going to be a different thing, which is going to be the following question. So the observation here is going to be the green precipitate. Green precipitate will be formed. And then the equation, so the equation simply is the iron H2O all 6, and it's an ion 2 plus the carbonate. That will give the iron carbonate plus the 6 water molecule, and that's a green precipitate. So now they say that the solution, which contains the iron 2 plus, the ion of iron 2 plus, it changes to a yellow-brown color after several hours in contact with air. That means it has then it changed from iron 2 plus into iron 3 plus. So in contact with air, it was oxidized into the other oxidation state, which is 3 plus. Now, when they add sodium carbonate to this yellow solution, what is the observation and what are you going to see, and give the ionic equation. So the observation, they didn't really ask about the observation, but the observation is the bubbling because there will be carbon dioxide. Now we need to write the equation. So here we are going to write the equation. So remember that we are talking about now the iron 3 plus. So H2O6 3 plus, not the 2 plus now, plus the carbonate 2 minus, and we would need 3 of the carbonate now. That will give you and 2 of the iron, so you can balance the equation. So 2 of the iron, H2O3 OH3 plus 3 CO2 and 3 of the water molecule. So what happened in this reaction is basically because the iron has with the 3 plus has high charge density, so it acts here more as an acid. It donates more of the protons from the water molecules that are the ligands, and this higher acidity will react with the carbonate to give carbon dioxide and water. So for each of the molecules of this complex, 3 protons will be given away. This is why we ended up with the iron hydroxide rather than with the iron carbonate, because in case of the iron 2 plus, we end up with the carbonate. This is another question from a 2024 paper, and this is from paper 3, and it's about the colored complexes of the transition metals. So this is a 6-mark question where they ask you about the complexes containing transition metals ion and why they are colored. So in the answer, they want you to cover 3 points. Explain why some complexes containing transition metals ions are colored, list the factors that affect the color, and describe how colorimetry can be used to determine the concentration of the colored complex. So let's start with the first one to explain why some complexes containing transition metal ions are colored. So we know that transition metal have d orbitals, and the d orbitals can actually split or they have different energy levels. So first point is that d orbitals have different energies, or they can split into different energy levels. And then you have to refer that electrons can move. So electrons move to the higher energy level. And when they move to the higher energy level, when will that happen? When they absorb, electrons absorb light in the visible region to gain energy and move to the excited state or the excited energy level. So now the color we see is the complementary color, or the part of the color that is not absorbed, or the part that is transmitted. So anything that tells us that the part of the color or the combination of colors from the white color that hasn't been absorbed or transmitted are the one that we see. And this is the first stage, why they are colored. And then the second stage is to list the factors that affect the colors. So there are 4 factors affecting the colors. The first one is the metal ion itself. So first, the metal ion, or the metal in general, and then the oxidation state of the metal, and then the coordination number, and finally the ligand itself. So the metal, the oxidation state of the ligand, the coordination number, and then finally the ligand. And finally, they want you to describe how the calorimetry can be used. So the use of calorimetry. So calorimetry, how do we use calorimetry to determine the concentration of an unknown sample? So the first stage is to measure the absorbance of a range of known concentrations of the colored complex. And then the second stage for the calorimetry is to plot a graph for the concentration versus the absorbance, which is the calibration curve. And then the third stage is to measure the absorbance of the unknown solution, the solution of the unknown concentration solution, and use the curve or use the calibration curve to find the concentration. So you measure the absorbance and then use the calibration curve, because the calibration curve will give you the concentration over the absorbance. It's a straight line. So when you find the absorbance of the unknown one, you can find the corresponding concentration, as this is going to be the concentration of your unknown solution. And the second question related to this one is about the visible spectrum of the aqua ion of copper 2 plus. So use the wavelengths at the peak of the curve. So normally when we do calorimetry, we measure the absorbance at the wavelengths of maximum absorbance. So when you look at when you look at this curve here, you're gonna find this is the maximum absorbance, this is the peak, and this is the corresponding wavelengths. So this is the wavelengths we going to use in calorimetry. So they want you to calculate the energy and using this data. So first of all, you need to find the wavelength. So the wavelength here is equals 800 nanometer. And we need to change that into meter, because when we calculate the energy, we need to use it in a meter. So then it will be 800 times 10 to the minus 9 meter. And then delta E, or the energy, will equal the Planck constant, and this is multiplied by the speed of light over the wavelength in meter. So Planck constant provided here, 6.63 times 10 to the minus 34 times the speed of light, which is 3 times 10 to the 8, and this is divided by the wavelengths, which is 800 times 10 to the minus 9 in meter, and that should give you the value of the this value here. So it's going to be 2.49 times 10 to the minus 19. In 2023, the question about AQAN was about aluminium. And the first question in this one was to give the electronic configuration of aluminium ion. So when you give the electronic configuration, don't forget to remove 3 electrons. So the electronic configuration is 1s2, 2s2, and 2p6, because the 2 electrons in the 3s2 and the 1 electron in the 3p1 are removed, because this is an ion. When anhydrous aluminum sulfate is added to water solution, the solution formed will contain the complex aluminum ion, which is Al, and with 6 water molecules. Give the equation for this reaction. So this is like a substitution. So we're going to substitute the sulfate with the ligand, which is water this time. So the aluminum sulfate, and then we need to add the water molecules. In this case, we're going to add 12 molecules of water, because there are 2 atoms of aluminium here, and we would need to give 2 of the aluminium complexes. So aluminium H2O6, each will 6 water molecules, of course 3 plus, and this is plus the 3 sulfate. Explain why the solution containing the aluminum aqua ion is acidic. This is because aluminum, and this is the same for aluminum and also for the iron 3 plus. So aluminum has high charge density, so it weakens the OH bond and the ligand and the water ligand and donate a proton. So that's why the solution is acidic. State why the concentration of aluminum sulfate solution cannot be determined by colorimetry. Colorimetry can only be used for colored solution. Aluminum is not one of the transition metals, so their complexes are not colored. Aluminum aqua ion is not colored, and aluminum sulfate solution is not colored. It's colorless, so cannot use colorimetry. So because it is colorless. An excess of aqueous ammonia is added to a solution containing the aluminum aqua ion. Give an ionic equation for the reaction and state one observation. So in presence of ammonia, whether it's going to be concentrated ammonia, whether it's excess or just some of the ammonia, the product will be exactly the same, which is the aluminum hydroxide. And the aluminum hydroxide is a white precipitate. So the observation is a white precipitate is formed, and then the equation is going to be the aqua ion of the aluminum plus the ammonia. So we're going to need 3 of the ammonia, and that will give us the precipitate of the aluminum hydroxide, 3 of the OH with 3 of the water molecule, and 3 protons will be given to the ammonia to give 3 of the ammonium ion. An excess of dilute sulfuric acid is then added to the product of the reaction in the previous question, which is the aluminum hydroxide. Identify the aluminum species produced. So remember that aluminum hydroxide is amphoteric, meaning it will react or act as a base in presence of an acid and will act as an acid in presence of an excess of a base. So in presence of the excess of the acid here, so the presence of the sulfuric acid means there is an excess of an acid. So then it will give us the aqua ion of the aluminum. So it will dissolve in the acid. So the product here, the aluminum species, is going to be simply aluminum with H2O6 3 plus. So this is the product. Then this is the structure of the editor for minus ion, and there are atoms of 2 different elements in the editor that can form a coordinate bond in an aluminum ion. So they want you to draw a circle around the ions of the 2 different elements. Remember, in the editor, we have the 2 nitrogens and the 2 oxygens with the negative charge. These are the 6 atoms which are going to make or form the coordinate bond, because this is a hexadentate ligand. So you simply should circle one of the nitrogens and one. In 2022, the question was about copper and copper complexes. So the first question was to explain why an aqueous solution containing copper chloride to minus ion are yellow. Remember that these are transition metal complexes, and they absorb light because they have the d orbital. So the answer here is because the light is absorbed and the electrons are excited. So yellow color is transmitted. Remember that this is the complementary color of the wavelengths, or the color of the wavelength that was absorbed when the excitation took place. And then this is about the energy absorbed, how much energy is absorbed, or the energy change. So here, when the d electron move from the ground state to the excited state in the copper complex, the energy change is this. So this is the delta E, and they give you the Planck constant. I want you to calculate the frequency in second minus 1. So we know that delta E equals h times mu, which is the frequency. So that means mu here will equal the delta E over h. So let's just put that here in this equation. So delta E is 3.98 times 10 to the minus 19, and H is 6.63 times 10 to the minus 34, and that will give us the frequency in seconds, which is 6 times 10 to the 14 second minus 1. State three ways in which transition metal complexes can be changed to alter its color. There are three ways, three things that you can change and would change the color of the transition metal complex. The first one is a change in the oxidation state of the metal. So if you change the oxidation state of the metal, the color of the complex will change. Or if you change in the coordination number, or finally, if you change the ligand, so change in ligand as well. So all of these changes will change the color of the complex. And then consider the following reaction scheme in which PQ and R are different complex ions of copper. So we started off with the copper 4, 2 plus aqua ion. And then the first one is the formation of the complex P when they react with excess water, and Q when react with excess aqueous ammonia, and R when react with sodium ether. So the first question here is to name the shape of the copper chloride, copper Cl4 complex. So this is a complex with 4 coordinate bonds. So this is going to be tetrahedral. Remember that chloride is quite big. This is why there are only a maximum of 4 chloride atoms that can surround the central metal. So it's always going to be tetrahedral. Give an ionic equation for the conversion of a copper chloride to the complex ion P. So complex ion P, when we add excess water, it's going to be a displacement reaction. And this is going to give us the copper ion, which is the aqueous copper ion. So now we have the copper Cl4 2 minus plus the water molecule, the excess, we need 6 of the water molecules. That will give us the copper with the water, 6 of these, and now the copper will have a 2 plus charge plus the 4 chloride ions that were released. State the color of the solution containing the complex ion Q. So complex ion Q, and they want the equation as well. Give the ionic equation for the conversion of this to Q. So when we add excess of the aqueous ammonia, remember in case of copper, what happens is that it will give you the deep blue solution because there will be substitution with ammonia. But remember as well, if you just add hydroxide ion or you add a little bit of the ammonia, that will give you a blue precipitate of the copper hydroxide. And because we added excess of the ammonia, so the color here will be deep blue. And then the ionic equation is going to be the copper chloride here to minus plus the ammonia. You would need 4 of the ammonia because there will be 4 ammonia surrounding the copper, plus the water, of course, because we're still going to have the water, and we would need 2 of the water. That will give us the copper with 4 of the ammonia and 2 of the water, and the charge here will be 2 plus. And now all the 4 chloride are released. Identify complex ion R. So complex ion R is simply the copper with the editor. The editor, the charge is 4 minus, copper is 2 plus. So this is going to be the copper with the EDTA or editor, and the charge here is going to be 2